Hello, and today we're talking about the structure of benzene. So first off, we're going to talk about how the structure of benzene was first discovered. So a guy named Kekule proposed the structure of benzene was C6H6, and if the carbon-carbon double bonds were present, then the benzene would react in a similar way to alkenes. And also, each carbon-carbon double bond would be expected to react with bromine water, therefore decolorizing it if it was in solution. However, neither of the two things happened in benzene. So he came up with his equilibrium model, which stated that the double bonds were in constant equilibrium, and they were in different positions all the time. So it's better to use the circle to represent that the delocalized bonded electrons are going round and round and round and round, always in a constant state. So, but he first proposed that they were always in state 1, this one, or state 2, this one. So he refined the proposed structure of benzene to suggest that benzene had two forms, and they were both in dynamic equilibrium, form 1 and form 2. They were in such rapid equilibrium that the molecules could not react with a double bond, as the position was constantly changing, which is why we use a circle. Carbon-carbon bonds and carbon-carbon double bonds have different lengths. Catherine Longsdale found that all 6 carbon-carbon bond lengths are the same, which is about 0.139 nanometers. Using X-rays, the bond lengths of carbon-carbon bonds and carbon-carbon double bonds were different. Carbon-carbon double bonds are 0.134 nanometers. This suggested that the proposed structure of benzene was incorrect. Kekule also came up with the idea because it was like a snake eating its own tail. Bizarre, I know, but that's how he came up with it, apparently. I don't know, I'm not Kekule. So now we're going on to the hydrogenation of benzene, the actual chemistry behind this. The Kekule structure of benzene contained 3 carbon-carbon double bonds. The chemical name for this would be cyclohexa-1,3,5-triene, or 3 double bonds. But when an alkene reacts with the enthalpy change of hydrogenation, or the energy change to put it quite simply, the enthalpy change of hydrogenation is negative 120. Negative meaning the reaction is exothermic. And Kekule's benzene with 3 carbon-carbon double bonds would be expected to have an enthalpy change of hydrogenation of negative 360 kilojoules per mole, so 3 times the amount of each cyclohexene carbon-carbon double bond value. So, yeah, that might be expected. But when benzene is hydrogenated, the experimental value of the enthalpy change is negative 208. So it's 152 kilojoules per mole less than cyclohexa-1,3,5-triene. The most important conclusion is that the real structure of benzene has much less energy than the Kekule structure. So this is called delocalization energy. So this is because of the delocalized electrons giving off a little bit of energy. So I've got 2 diagrams from the actual OCR textbook here to summarize for you. So Kekule's benzene is up at a higher enthalpy than real benzene. Real benzene is negative 208 kilojoules per mole, and so this will be cyclohexene, hexene 1,3,5-triene and all that. So really the real benzene should have a lower energy, and it does. Kekule's structure has a higher amount of energy, or enthalpy. This is a quick summary of the different reactions. So cyclohexene plus hydrogen goes to cyclohexane, giving off 120 kilojoules per mole, and the hydrogenation of Kekule's benzene, cyclohexa-1,3,5-triene, with 3 double bonds, so it needs 3 H2 molecules to cancel it out, so we'll have 3 times that amount of energy. So thank you for watching this quick tutorial on the structure of benzene. The next tutorial I will go into more detail about the delocalized model of benzene. That's for another tutorial. So thank you for watching.